bosonic string scattering, and I'll analyze some features of those results. And this is work done completely due to these two graduate students at Kanpur, Anurag and Shantanu, and it was published around August last year. And some parts of this work was already presented in TIFR in the pre-ISM workshop, so some of you might have been present. Yeah. So the one motivation is to for this work we are looking at excited states of bosonic strings, and the motivation is coming from black holes because we expect chaos to be present in black hole, and through scattering of these excited states I will define a notion of, so I'll just use a notion of chaos which has been used earlier, and it goes by the name of chaotic scattering. And one expects that black holes, for example the recent studies of SYK and some other low dimensional models have already established that the spectra of the matter, if there is a quantum black hole, it shows some level repulsion. There is a random matrix in there. In a full quantum theory, the observables, for example the S matrices, should also have signatures of chaos. And in fact this is where, in this chaotic scattering is where random matrices first got associated with chaos, quantum chaos. This was this observation by Wigner, where he looked at the neutron scattering through heavy nuclei, and there were the S matrix showed resonances, and those resonances can be interpreted as the hadronic spectra. And then if you the nuclei Hamiltonian will be too complicated, but if you make an ansatz that it is a random matrix, then you reproduce almost the correlations that you see in the data.
Is that almost the same as just asking about statistics of energy eigenstates?
Yes.
It's
Yeah. Yeah, but you need an ensemble, so you need many of these resonances. So, and the ensemble is created by changing the quantum numbers of the nuclei in some way. So if I change that, then I will get a different set of resonances, and then I can ask if is there a correlation among those energy levels.
But to the extent that the S matrix contains information about the spectrum,
Yeah.
the fact that there is signs of chaos in the spectrum means there are signs of chaos in each.
That's what one will expect. Yeah. So in the case of string theory, we are computing the S matrix, which is the S matrix of the target spacetime theory. So it will have information about the spectra of the target spacetime theory, which is some interacting quantum theory. And okay, there is this. I'll not go into this. So there's also random matrices also appear naturally in the eigenstate thermalization ansatz, and one can wonder if I have states which are mimicking these black hole-like states, which have this some kind of a chaotic scattering feature, then one might wonder if the ETH also applies to those states. And string theory, because string theory will allow us even at tree level to explore these features. So I will talk about so there is already correspondence why these states might have something to do with black holes, at least some features. It shares some features with black holes, and then I'll talk about these states in bosonic string theory. One can also discuss these states in superstrings. Then I will present the results of the S matrix involving these states, and then I will analyze the results and show that there is a correlation. There is a random matrix correlation. And then I will, if I have time, I have many questions that I will like to hear your opinion about. Okay. So the proposal was that small black holes are free strings. This was an entropic argument, that basically the entropy matches, and the way this goes is you first equate the masses. So a free string, so the mass is just given by square root n over alpha prime, where n is the level of the free string. Now keep reducing the size of the black hole by tuning the string coupling, and then one can show that at some point the entropies will match. And this will exactly happen when the size of the black hole is that of the square root alpha prime. And little more concretely how it works is, if I consider, so this is heuristic, it doesn't get the entropy factor of 4, A over 4 g Newton, but it gets A over g Newton in this way. So so this is my g times m black hole is the radius of the size of the black hole, and g in string theory is g string square alpha prime. So if I set them equal, and m black hole I have already equated with the m string, which is square root n over square root alpha prime, then I get that the size, when the string size becomes that of the black hole size, is when the string coupling goes like 1 over n power 1/4. So that means if n is very large, if I am considering very large levels, then the string is free. And if you compute the area over g Newton, that's r square over g Newton, that has the same Cardy scaling of entropy. So in that, if you plug in these factors of this particular g string square, you get square root n. So that's why it's an entropic argument. It doesn't get the factors right, and also this is truly free. The string is truly free only at n equal to infinity. But at any finite n, the string is not free, and it's actually non-perturbative. So to see some features, you can't get it from tree level string theory. Yeah.
In higher dimensions.
Higher dimension, there is a generalization by Polchinski and Horowitz. It also works out.
GS by 1 by root n changes.
Yeah, this will change. There will be a d-dependent factor.
I'm just curious.
Yeah.
If you compute the one loop correction to 4-point scattering
Yes.
for a excited state,
Yes.
with a large, where G string is of order.
Yeah.
Are the one loop corrections small?
So for this has not been done for excited states. There are some issues. Yeah, it could be.
Really excited that
Yeah.
being misled by this value.
Yeah.
That
Could
is
be.
a concrete
Yeah,
calculation.
that will be a concrete calculation. Yeah.
What is the concrete calculation?
One loop.
Is the
One loop correction, small.
The 4-point scattering for highly excited states.
Yeah, I will have some
Of
comments.
this value.
Yeah, I will have. Yeah, is it suppressed in n or something in the level?
Yeah.
Yeah. So I'll talk about the states. So these are the DDF states, which are also explained in quite detail in GSW. So you start with a tachyon and you hit it with a photon vertex operator, and then you do a OP. Once you do a OP, you will get many states. Then you do a contour integral that will project to physical state, and this you can repeat and create excited states. So that's the logic. And in this way, one can move units stepwise. One can also directly excite with a higher frequency, and in this way, one can get a complete set of states. What is the? Oh, repeat this process. So on this, you do the same thing. So finally, the state looks like this. So you have a simple string, and then you bombard with these vertex operators and do the contour integrals. This entire operation can be actually written as an operator. So one can do the contour integral, and this is what of the OP, and this is what one will get, which involves derivative of x and Schur polynomial of derivatives of x. And this comes with, so each of these are photons, so each of them have polarizations. So that gives the net polarization of the state, of the excited state. So if one does a SOD minus 1 irrep decomposition, one can get the spin basis states. And the mass squared is related to this party. So each of these photons now I can choose to be of different mode numbers, and I can have different numbers of different mode numbers. So the level is given by the the partition sum. And yeah. Then you can map these to light cone states.
But then you will just automatically get the right.
Then you will get automatically the right state. Yeah, and this description is something in between light cone and covariant. So this allows you to match to covariant amplitudes. We'll see. and the sum of the length of the partitions turns out to be the spin. No problem. So basically, for example, if I want to create a very rapidly spinning state, then I choose basically all these ends to be large. That can happen if my R, there's only one R1 which is 1. And then this, so then it's basically a minus 1 n times. So that's the reggae state. That is the state in the leading reggae trajectory. All the R's are 1. That will give the longest partition. 1 1 1 1 1. So that's the reggae state. That corresponds to the reggae state. And this state will be indeed special in the scattering that we will see. Okay. So Gross-Rosenhaus considered these states 2021, and then with 2 tachyons they computed the amplitude, and then Bianchi, Firota, Sonnenschein and others they computed with 1 more tachyon. And if you consider the 3-point amplitude HTT, H is for the highly excited state and 2 tachyons, then the kinematic choice they made was the simplest one, like decay. You have the heavy state sitting here. It has some polarization which is dictated by the momentum direction of the photon, and then it decays. So there is one angle, one kinematic variable, angle, between the polarization and the decay direction, that is chi. So this amplitude only depends on this variable, and this is the answer of this amplitude. So J is roughly the spin of this, and N is related to the mass of the state. Okay, and then they didn't really, they said that this, they made some plots and it looked irregular. So they said there might be some random matrix correlations hiding in these things. So which was made precise, and which we also studied with taking 2 of these heavy states. And that allows us to also compute some thing, means because this amplitude I can think of evaluating like a decay, actual decay, where the final state still has a heavy state.
So what plot did they make?
So plot they made was similar to this. So the amplitude as a function of the scattering angle. Yeah. Yeah.
I mean, if I think of it in the kinematic regime where it's one heavy decaying into a heavy and light.
Yes.
Then I just do it in the center of mass.
You center of mass,
And
yeah.
It's just back-to-back decay.
It's a back-to-back.
What's the angle?
Angle, the polarization. There, the heavy state has a polarization. That's why there's an angle.
Polarized.
Yeah. That's why scalar amplitudes don't show any chaos.
Right.
And this was a paper from 2 days back where they studied, Pesando studied the scalar amplitudes. There is no chaos.
So it's the angle between
Yeah.
the direction and the,
Yes. Direction of the polarization and the back-to-back things which are going, the decay end products.
That's supposed to show chaos?
The dependence of the amplitude on that angle.
Will be chaos.
Yeah. But in 4-point you really have Mandelstam variables. There you can actually plot against Mandelstam and get these peaks.
4 point will be much
Yeah. So the contraction yields, there's some combinatorial exercise one has to do to compute this. So I'll just show the show the results. So here what I'm doing is I have some yes.
Let's say we do this exercise in field theory.
Yes.
By similarly taking some highly excited
Spinning state.
yes, and then just in a case theory.
Yeah.
What is the answer you get?
So basically, yeah. So there you will. So I think what I remember is you don't get so many peaks because the peaks are somehow resulting because there are many bound states. And in perturbative field theory computations, you don't have any
I see.
bound
Good.
states.
So you're saying that this all appears because perturbation theory mixed up.
Yeah.
Why does string perturbation theory work? Why is it that we can't use string perturbation theory? Why don't the G-string corrections and so on become important? Yeah, this time, why does string perturbation theory work?
Work for showing these features.
Yeah. Whereas gauge theory doesn't work.
Yeah. So the
What was the
perturbative gauge theory.
You can take some highly excited state maybe in a gauge theory. You just act with
Yeah.
lots of highly excited Fock space states.
Yeah.
And then you scatter some light glow on
Yeah.
it.
So I think if one does some resummation, then one will see these structures.
No, actually, it sounds right to me that if the number of the excitation is much larger than inverse of the coupling, and
Yeah.
then perturbation theory will break down if the number of photons you have. But here, is that the case that the number of things is larger than G string, or no? You don't need. You can take G string to be as small as you like.
Here, yeah, essentially 0 because I am doing tree level. But
Exciting to a level. Okay, at least for the correspondence point argument.
yeah, then
Not sure.
yeah,
Otherwise, you can dial them independently.
yeah.
Yes. So here you're exciting the level which is probably so that the inverse of the level is still larger than G string.
Yeah, that is true. Because G string goes like 1 over n power 1/4.
I see. 1 over n to the power 1/4. No. That's too large. Then you would worry that all sorts of G string corrections will also matter. I was thinking of dialing them separately.
Oh, separately.
Best to because if
Okay.
you go to the
Correspondence point, then it is non-perturbative.
I
Yeah.
think.
Then I would have thought all corrections would be.
Yeah.
Yeah, that's
Yeah.
why I was asking that original question. But I think just dial it independently. For his purpose.
Okay, but then what is the qualitative difference that in string perturbation theory you can see signs of chaos, whereas in field theory?
In field theory,
But I mean, in field theory, if you have a coupling, you can dial independently.
I think he's saying
Yeah,
that
but
it will
it-
look like free fields with a small coupling, and you will not see all this data. You will not see all these.
all these some of these are features of having many almost bound states, almost quasi-stable states. But those states in a regular field theory are very non-perturbative.
So either you're close to the Fock space, in which case you don't see chaos, or you're.
Or you have to be close to some very strange background.
And in string theory, you just see it. You just act with these
Yeah.
PDF operators, and you just see it. It sounds very strange. What
Because
say
you
you
have
should
these
say?
highly excited states here, right?
Yeah, there are many.
Even the infinite
Full
power that
string, free string has the.
This is the sign of all the free strings.
The
Free strings.
We have highly
yeah, highly excited states in the
Yes.
free string spectrum. Yeah, but these will be some, but the resonances which show up will be something, should be some states in the target space time.
So they are not these the free strings.
Yeah, these resonances won't be free string states.
So I'm very
The states which would correspond to these peaks.
yes, I'm very confused why string theory is working so well. Like why is it here?
The states
Yeah, so these states the only the asymptotic states which I am scattering, those are the free strings. Those I have constructed in free string, and then I am interpreting the resonances as some quasi-stable states in the target space time, and that
strings, right?
it's made out of strings,
But they decay.
but they
But at tree level, the resonances will not have any width.
No, they have.
width.
That's what's very confusing. How is
They
that?
have width.
But at tree level, how do you have width?
Yeah, so this is, but this is, that is,
Which is somehow 1 over n or something, controlled by your parameter that your highly excited state parameter.
yeah. So so actually, so this, so no, essentially, I think these probably don't have it. This is done with some
I epsilon.
regularization. Yeah.
You could have it. So you could come with, if you have lots of these DDF particles, you have lots of complicated kinematics. You could get something that looks almost like a pole.
No, but the spectrum doesn't have states.
But this is
all
not
at
the
once.
string spectrum. I thought he's saying this is just, you just take the asymmetrics, you plot it
Yeah.
as a function of this angle, and you'll find sometimes it becomes large, sometimes it becomes small.
But he has the amplitude in somewhere. He
Yes. There is the amplitude.
Those amplitudes don't have branch cuts, right?
No, these amplitudes only have, these amplitudes don't have branch cuts. These are perfectly regular amplitudes. But these have almost these have regions like here, which almost behaves like a resonance.
How do you know this amplitude can have this resonance?
Which one?
This amplitude he shows. Some complicated amplitude, some many.
Well, if
many,
you have something with a width, usually you have. I mean, that's an indicator of a branch cut, right? He's saying that these only have
plus a
poles.
squared, I would have said is some resonance around x equal to 0. Like it's
What, sorry?
I would would have just written like 1 by x squared plus a. Maybe somewhere along this way you had 1 by x squared plus a squared, and it looks like something that kind of goes up and comes down around x equals 0. So it has some weight which is equal.
Extreme amplitudes can only get poles, right? They won't get branch cuts.
Exactly.
I mean,
There's no branch cut.
yeah,
There's no branch cut.
But you shouldn't get a width either.
Yeah, exactly.
Tree-level
That's
Why not
amplitude.
1 by x
Because
squared
they are
plus a?
imaginary paths. They can only
There,
cut
there,
things
there,
down to
yeah.
round.
There's no branch cut.
Cutting relations.
There's no branch
So,
cut.
I mean, I would be that.
Yeah.
That's why I'm surprised
Yeah.
about that plot. I mean,
There's no branch cut, but okay, but these oscillations are present in the S matrix.
it just
Yeah. Yeah.
Kinematics is, of course, you're back to back, but then the polarization of the initial heavy and the polarization of the final heavy, right?
So okay, no, so yeah, these are independent, and it also depends on, so this is, so in that case, you see there is also this dot product, yeah, there should be a zeta 1 dot zeta 2 here.
Okay.
So then there are actually two angles here.
Yeah,
In this case, there are two angles. In this, and it turns out that if I choose the polarizations of zeta 1, zeta 2 to be orthogonal, then it is less random, these plots.
Okay, anyway, but
Yeah.
in one of those two angles, you get that seemingly.
Yeah, this at some angle.
Plotting versus the scattering angle, not against the center of mass analysis.
Together I'm
No, this is,
Energy, you see delta functions.
yeah.
But if you plot it against a scattering angle, you can see smooth graphs.
Okay, but I should be able to, in the center of mass, this is one of those two angles.
Yeah. So, this is the one confusion is arising because we are trying to relate the positions of these oscillations to the
Yeah, that's
to the spectrum of the target space-time theory.
Yeah.
So that unless we identify really those states, we should.
That's different. Forget about identity.
yeah.
I can believe that you do a very complicated scattering with lots of kinematic data,
Yeah.
and you plot it as a function of one variable, and you can get some features like this. I think this is okay.
yeah.
You just have some very complicated function. You take some cross section of it, and maybe it will look like this.
Yeah, it is not an S. It's in scattering.
Yeah.
So this width does not correspond to the width of a particle.
Yeah, it's just something. It's
some feature.
Just a feature.
But but one thing I want you to notice is that if I keep the rest masses of these highly excited states fixed, but change the quantum numbers, then they look very different. So this one, so both these plots are for the same capital N value, N1, N2 values.
And you're going to interpret this as evidence of random matrix statistics.
Actually, one can identify random matrix statistics by looking at where these oscillations have peaks. I make a list, and I show that list has features of a random matrix eigenvalue distribution.
So as a function of angle,
Yeah.
you find it's chaotic.
Yeah.
Just curious, you're going to study the location of peaks.
Location of these
You would
peaks
also study the
heights or
not just
the
the heights but the widths also.
yeah, but the widths as we are discussing, we don't know whether one should.
Curious
Okay,
whether
what
that will show anything.
that any chaotic feature? Yeah, that.
This is a real graph, by the way. Or
Yeah, real graph. Real.
Real graph.
Yeah, it's an analytic function.
with some possible choices of those.
Yeah, with these choices, with these choices.
I see. So with this choice, you.
Yeah, with these partitions. Yeah, the amplitude is totally real.
I
Yeah.
don't understand why you should compare this graph with eigenvalues of random matrices. Where does that? I mean,
Oh,
this is so as we
Yeah.
figured, this is not energy. These are angles. So
some angles.
where does random matrix? So that random matrix would model what?
So yeah, so the random matrix would model basically where we have peaks in this S matrix.
Where the detector clicks the most.
Yeah. Okay, and this is what you get. So you do exactly that operation, and if you take the result HTT of Gross-Rosenhaus then you find convergence to, as n increases, it really converges to GOE or GUE. So this is a better fit. So here this is just a one parameter distribution of the level statistics. So C equals to pi by 4 is the GOE value. So and then as n increases, it oscillates around this GOE value. And one way we understand why in the HHT, if we get convergence to GOE if both the H states have exactly same partitioning. If it's exactly the same state, so the scattering configuration has time reversal symmetry. So and that's why we have convergence to GOE, because the GOEs are ensembles for time reversal symmetric cases.
So you take the two heavies to be the same.
To be the same, exactly same. If you deviate, then you move from GOE to GUE.
I have a suggestion actually.
Yeah.
So maybe we can. Let's say we take the same thing in the gauge say thing that I was asking, and we use these CHY relations, which just compute this large number of scattering amplitudes. It might not be surprising if you get the same behavior. You just take one variable, one gluon, and you call it angular.
Yeah.
Take the rest and you call them heavy, and one of them light.
Amplitudes are complicated enough to have.
Yeah, because the amplitudes are by these solutions of these CHY equations. In fact, there's the same equations that govern string scattering in the ultra high energy.
Okay.
Level. Exactly the same equations.
Okay, then.
And you get lots of them. You get n factorial of them. So you're just summing over n
Yeah.
factorial complicated things, and maybe you get this.
You get some random matrix.
But I thought the spin of the external particle was crucial in your story.
Yeah. So because So if for example if it spins 0, then there is all these features go away.
This will be spin 1. I'm just talking about gluon scattering. Now will be gluon to gluon scattering.
Yeah.
What is it?
Yeah. So
Moreover, in your case, you can have many invariant angles in momentum space also, right? Because
Yeah, but
there are many coming
I'll
in
call
between.
end of the momenta, I'll call them heavy, and the one extra one I'll call the light one.
Yeah, but
And then I'll use.
I mean, in that spirit, you can have many invariant
Yes, you
angles.
can have any.
In your construction, you cannot project to the spin 1. Can you?
one can, this has not been done, means to go from the DDF systematically to the SOD minus 1 irreps, it's being done now.
Actually, frankly, it's not clear to me why there are not the same invariant angles here, because your DDF operators have all these degrees of freedom, right?
Yes.
So you can think of them also as having, having
It's
lots
some
of-
superposition,
Yeah, lots of different kinds.
lots of different.
So you just happen to choose a particular basis. But
Yeah.
I could have written this in the momentum basis.
Yeah.
And the same invariant angles that exist in the example I mentioned would exist there. No? What's the difference?
Just for three-body decay, there aren't. That's all.
No, but this is not 3-body decay. This is DDF operator.
I
It's
mean,
actually
1
made
to
of lots of partons.
1 to 2.
This is 1 to
These
2.
1 to 2. So 1 to 2, there's nothing else.
We have heavy, light, right?
Yeah.
But heavy is actually this DDF
Yeah.
thing. But that's actually made of lots of partons.
Composite, one can
It's not really
think
a
of,
individual
but
element.
There's no center of mass momentum.
it's one center of mass. It's as one particle in that way.
So you can do more.
Can I
Yeah.
suggest that
Yes.
allow me to proceed
Yeah.
and then
Okay, the approach to RMT is faster if they are not orthogonal. These two things are not orthogonal. And this is the 4-point function. And the 4-point function, this is written in the gross Mendel limit, but 3 level. So just fixed angle high energy limit. So it's the Veneziano. So here chi is the scattering angle. So it's the Veneziano convoluted with some dressing. And the Regge limit, one can check that it respects the bound.
you show them some special
Some
mass,
yeah, center of mass polarization. And you see so in the Regge limit, you see that the exchange behaves like a particle with a average spin, J1 plus J3 over 2. And this is the usual thing one gets from Veneziano. So all these factors just give this in the Regge limit. Okay, and even here one finds this erratic behavior because it's essentially the Veneziano multiplying that 3-point function. with some convolutions.
Now this is 2 to 2.
This is 2 to 2, 2 heavy, 2 tachyons.
Oh, 2 heavy, 2 tachyon.
Yeah, heavy tachyon, heavy going to heavy tachyon.
One
Yeah.
heavy, 1 tachyon going to 1 heavy, 1 tachyon, right?
Yeah, yeah,
That- okay.
yeah. That is the kinematics. And okay, and then going back to this 3-point function, one can also try to study some asymptotics, and one can, for example, one can do a coarse graining over all by keeping the mass fixed. So I coarse grain over all partitions. So if I coarse grain over all partitions, that can be done analytically by saddle point. One gets this function. So which curiously this this function, this dialog function, has a peak at pi by 2, which is exactly pi by root 6. So if I sum over all angles, if I want to consider a symmetric scattering coarse grained answer, if I sum over all angles, then it's 1 plus some e to the power minus square root n thing. So the leading answer, leading behavior doesn't have any n dependence. It's independent of n. Okay. So the leading answer doesn't have any n dependence, and remember this is computed, this is just the tachyon in this heavy background. So now there's a very heuristic consistency check with 1-point functions, thermal 1-point function, which, yes.
So it became a tachyon scattering of that heavy background. What was, I didn't
Yeah, so this is heavy, so a heavy tachyon. Now I am interpreting this as a 1-point function of tachyon in the heavy state. No, this is, I am going back to the 3-particle, HHT. Yeah, sorry.
So what do you mean by diagonal partitions?
Diagonal partition, I take exactly this is the time reversal invariant configuration. So I have exactly the same DDF state on both sides.
Oh, I see.
Yeah. And here this and what I showed you is that because of that function, this dialog function, that at pi by 2 this exactly cancels this pi by root 6. So at leading order this is independent of n. So this thing one can interpret heuristically as if I think of this as a 1-point function of a tachyon in this heavy state, then it should the thing which controls this the magnitude of this is the time to singularity. So this is roughly from this works by Greenberg, Mallasena, and Justin and Srijan. So here and this the time scale that you get for Schwarzschild, that is g newtons times the mass of the black hole, and that also doesn't depend on n, because at the correspondence point the factors of n exactly cancels. So it's some heuristic check of that expectation.
But is it known that, what is the logic behind saying that the DDF should be approximated by a single black hole and not a...
Yeah, it's not known, so that's why it's a heuristic thing. Okay, but this is a little more concrete, which is there's a way to get a classical limit from a spinning amplitude. There's this KMOC relations where one so now for classical limit, what one does is one scales the momenta. So usually one looks at scattering with massive spins, some massless particle of momentum k, and then so one scales this momenta with h bar, takes h bar to 0 along with s to infinity such that h bar stays finite. So this defines a classical limit for this amplitude, which can be identified with some classical objects in GR. Okay, so for example, this paper showed that that one can write down well-behaved 3-point amplitude in quantum field theories, where if you do this operation, you get the stress tensor of the Kerr black hole.
What is the accuracy? You do what of-
You take this amplitude, which they wrote down by like a bootstrap ansatz, and then you take this classical limit, which is you scale h bar to 0 and s to infinity, keeping h bar s fixed. Then what you get is the Fourier transform of the Kerr black hole stress tensor.
This is like this Gary Gibbons story of getting the Schwarzschild black hole using the graviton scattering.
I don't know about
You know,
that story.
This, I think it's Gary Gibbons. There was this old challenge by Salam, I think. Can you get the Schwarzschild metric by looking at scattering?
Okay.
And this seems similar, except they're getting curved.
They are getting Kerr.
Must be, you know, so they look graviton scattering and they try to compute the potential, and they were able to get out the Schwarzschild metric, whatever.
I see.
So maybe this is.
But this I think is
This-
amplitude. Some kind
This
of-
amplitude.
it's like that, what you're talking about is actually constructing the potential. This is I think more like an algorithm.
Is it different? Like you take this amplitude and you use the amplitude to get some metric.
I mean, this I think is some prescription, right? I mean, the Kerr stress tensor is that k nu type thing that comes in the.
So you get e to the power k dot a basically. That's the Fourier transform of the Kerr stress tensor.
What do you mean by Kerr stress
What
tensor?
is first stress tensor mean for?
Yeah. So
Kerr Neumann stress tensor?
yeah, Kerr Neumann. So you
Charge.
yeah with charge. So then you get then the scattering amplitude will have epsilon mu, t mu nu, epsilon nu. Then you take Fourier transform of that. That will give you this factor e to the power k dot a.
Tensor of the whatever tachyon field, right?
So
The light
stress-
field.
stress
No,
tensor-
stress tensor of the black hole.
I thought this stress tensor of the electromagnetic. I mean, there's some this is a charged black hole, so there's some electromagnetic field. I thought this E square minus B square.
So there are.
Sorry, I might be saying something wrong. Yeah, that's what I have.
Is it charged? Why is it charged?
So-
I thought you just could have taken it.
Yeah, so you could have done with without charges, but so in our calculation we did it for the open string, and we did it where we coupled the photon.
Then what is Kerr stress tensor? Let's say
So then that's called the square root Kerr stress tensor. If you square it, you get
It's
the
world
Kerr
line stress tensor. Like you model it
as a
the Kerr black hole. The field outside the Kerr black hole, you write it as a world line.
I mean, like I
Model the Kerr
Black hole is a point particle.
as a point particle.
Such systems that you have to give to that point.
oh, I see. Oh, that's what it. So,
Yeah.
so what I was saying was completely wrong, but I see.
Yeah, I'll just but for the string, if I take the Regge states and the string photon vertex and do this operation, then what I get for these coefficients are these numbers, and these match with superstring calculation, which was also done for superstring Regge states using a computation of Schlotterer from 2010. And there what one gets is the sum of these two Bessel functions, and this is exactly the stress tensor if I have a rigid string which is rotating with a charge at the end point, and that's natural that it's related to the Regge, because the Regge state corresponds to a rigid rotating string. So one question will be, okay, and if I do a doubling, then I get the Kerr. I get the Kerr for in field theory in their ansatz, but here I get something else. I get square of this function. Okay, this I'll skip. Okay, I'll just go to some questions. Okay. So, yeah, this was the question which you were asking, that subleading order in G string. First we were expecting to do the calculation just for the mass shift of these DDF states. So this was some work we are doing with Mrityunjay, but because this is bosonic, there are lot of IR divergences. So this has already been quite some time we are struggling with this calculation. So only some n equal to 1 level we could do, and the vacuum. Okay, and then this was the question that we saw that we could get the rigid rotating string. So if I now go to the subleading Regge trajectories, does this string start to do something more funny? So does it go to any classically chaotic configurations? So that will be interesting to understand. Okay, and then in 2D gravitational setups, there is a question: can we have chaotic scattering? So in setups which Sandeep was talking about, if I now look at many wave packets and scattering maybe close to the singularity or somewhere, can we also get such features? Recently, there is a technique developed to get S matrices for Liouville CFTs, and we are trying to, and this has been generalized now to the 2D black hole sigma model, and this we are trying now to see if such features are present also in these S matrices. And also, as Arnav also mentioned, that chaotic scattering in these blackish holes. And okay, and then there is also a conjectured relationship between that the modes have to respect, because of if they are scattering in a black hole background, that there should be some time delay effect. So that imposes some constraints on the S matrix. So what will be the analog computation using DDF, which will show this? That's another question. Thank you, and thanks to Anindo, Chetan and Justin for organizing this.
Maybe a couple of quick questions, yes.
So whatever the string version is infinite.
No, Regge string is the DDF state where you create it with these one partitions. So it's a state made out of.
He was asking what do you mean by rigid string?
Oh, rigid string. Sorry, rigid string is it's a particular embedding where the string is just straight and lies on a plane always and rotates.
The classical solution to the string equation somehow.
Yeah, string equation which respects the Virasoro constraints. Classical.
Have a charge at the endpoint.
Charge. You know that you put it there, and because of the charge you have a current. So then here in this case the amplitude is just epsilon dot j, and the Fourier transform of that for this configure for this j is the sum of Bessel functions.
Any other quick question before we break for lunch? Okay. So let's